Hello everyone, welcome to the mind map of Kinetic Theory of Gases, which is a precursor, I would say, for the chapter of thermodynamics, um, because we will deal with some tools which will be very useful in the chapter of thermodynamics. For example, the ideal gas equation. Uh, Coming to first of all, how we derived the uh, ideal gas equation because of several scientists you conducting experiments for which they derived empirical relations between the parameters involved in the ideal gas equation, for example P and T. So as per Gay-Lussac's law, the experiment that he did was, let's say you have a closed container, and maybe here you have planted a barometer, and there's this gas inside. What he observed was, when some fire is put, or the temperature rises of the system, the pressure also indirectly increase or directly increases as the temperature rises. It is understandable because when we raise the temperature of the system, the individual particles now have more energy, more kinetic energy, due to which it will strike with the wall with a higher force, right? Because it has a higher velocity now, due to which it will have it will result into higher pressure. So pressure is directly proportional to temperature. As the temperature rises of the system, the pressure also rises. So this was Gay-Lussac's law. There's this Charles law who gave that, let's say this was a closed container, right? Closed container. Now this was also closed, but this whatever lid it has is almost free to move up or down. And this is atmosphere. What he did then was provide heat into the system, and he observed that as we provide heat into the system, the individual particles would apply more pressure on the lid, right? So, and the lid is free to move up or down, due to which it will result into the lid going up due to air molecules having higher velocity striking with the wall with higher velocity, imparting more impulse into it, due to which the volume of the system effectively increases, right? Whatever volume it has, and due to which he gave the law, Charles law, that volume is directly proportional to T. You have to consider some things here, that since this was a closed container, the volume must be constant, and since this was free to move piston or free to move lid, the pressure must be constant, because the as soon as the pressure increases inside the system, the lid moves up, so as the pressure is constant. In that case, volume is directly proportional to temperature. You have to also consider the conditions to apply these basic empirical laws, otherwise it will not hold good. And the third, Boyle's law, what he did was take another cylindrical thing and maybe add a piston, and as he pushed the piston down, the piston will reach here, due to which the volume has decreased. But the barometer inside it gave the reading that as the volume decreases, the pressure increases. So pressure is indirectly proportional to volume, and that's why he gave the Boyle's law. And you also have to consider the condition for this, that temperature must be constant. If the temperature rises or decreases, this law will actually not hold good. It will be violated. Now, coming to uh, pressures. Pressure, I told you, it is the result of, let's say this is the particle going with some velocity, striking the container and coming down. This has resulted into, let's say this is the lid, this has resulted into some force being acted upon it, and all these forces being acted upon it will result into some pressure, because the net force divided by the area, that's what you will do for pressure. So they will all apply pressure. Now there is this Dalton's law of partial pressure. What you first have to understand for this is what is partial pressure. Let's say there is this container in which there are two molecules, hydrogen and oxygen. Hydrogen, these are hydrogen molecules, and these are oxygen molecules. What this says is, uh, in a mixed system, of course you are able to calculate the pressure or estimate the pressure using a barometer. But what if this system only had, the system remained the same, it only had these hydrogen atoms, no oxygen atom at all? Then the pressure applied by these could have been estimated using a barometer. That is what you were calling as pressure due to hydrogen. And another system in which these molecules are not there, only the oxygen molecules are there. In that case, we calculate the pressure to be equal to pressure of oxygen. Then this law says that when you add them up inside the system, the pressure of the system is actually equal to the individual pressure of each of the atoms if they were present. अगर वो प्रेजेंट अकेले होते, मतलब कि सिर्फ उसमें हाइड्रोजन एटम है, सिर्फ ऑक्सीजन एटम है, तो सिर्फ हाइड्रोजन एटम की वजह से जो भी प्रेशर उसमें बन रहा है, दैट इज व्हाट वी आर कॉलिंग एज पार्शियल प्रेशर ऑफ द हाइड्रोजन एटम. और सिर्फ हाइड्रोजन, सिर्फ ऑक्सीजन एटम अगर उसमें रहता, हाइड्रोजन एटम नहीं रहता, कोई और भी एटम नहीं रहता, सिर्फ ऑक्सीजन एटम की वजह से जो प्रेशर बनता, उसको हम कह रहे हैं पार्शियल प्रेशर ऑफ ऑक्सीजन. देन द नेट प्रेशर ऑफ द सिस्टम, जो टोटल प्रेशर होगा सिस्टम का, दैट विल बी इक्वल टू इंडिविजुअल partial pressure added up for all the molecules and the gases. This is called Dalton's law of partial pressure. Okay, I hope this is clear. These has been, I think, clear. Okay, now coming to, I think before doing actual, this was actually before jumping into kinetic theory of gases. This was more of an obvious thing because you already have read about these in your previous classes about ideal gas theory. What we are going to do to discuss now is actual kinetic theory of gases. What this theory is all about is it takes molecules of gases, and uh, depending on the physical parameters of the gases, it gives you an idea of what are the physical parameters it will exhibit. For example, what is the pressure it will exhibit, what will be the uh, maybe velocity of the particles, what will be uh, the things that we require, the energy of the particle. Now, before that, what we need to assume is, before the kinetic theory of gases, the theory is built upon some assumptions. The first assumption is that all the particles inside the container are identical to each other. Exactly identical to each other. All right? Of any gas. Let's say I have put a hydrogen, then all the individual hydrogen atoms are exactly identical to each other. And then the if you have something called, let's say, any other gas, let's say water vapor, H2O, then it will have another uh, maybe size of another particle. Then what it says is the collision between these atoms and the wall, since they have initial velocities, and the collision between these atoms and the wall is perfectly elastic. In previous classes you must have learned about perfectly elastic collision, in which no energy is lost inside the collision, and whatever kinetic energy it had previously, it will regain the same. So it is perfectly elastic. All the collisions whatever are being performed with the ball or with the particle and the wall, as well as with individual particles as well, when they collide with each other, they are not losing any energy in that collision. Those are perfectly elastic. And when you take all these assumptions, and the other assumption is that all these particles of course can move in any random direction, since we generally have many amount of particles, right? We can't actually take one or two individual atoms and then do experiments on them. Whenever we take it is in trillions and more. So in that case, the direction of individual particles becomes almost random, right? If you have two particles, then you can say that this is going in this direction and this is going in this direction. But when you have so many particles, then it becomes almost pointless to even talk about the direction. That is why we assume that they have random direction of movement. These were the assumptions around which the kinetic theory of gases is built. ये assumption हमारा होना ज़रूरी है, अदरवाइज हम अप्लाई क्या करेंगे? अगर हम लॉ ऑफ कंजर्वेशन ऑफ एनर्जी लगाना चाहते हैं तो हमें बताना पड़ेगा ना कि इलास्टिक कोलिजन हुआ है, अदरवाइज हम लगा ही नहीं पाएंगे. सो दैट इज वाई हमें थोड़ा सा assumptions लेना पड़ता है टू बिल्ड द मॉडल which is the kinetic theory of gases. Now, the basic first thing that is associated with it is energy associated with first of all, let's just take this part first because it talks about something called degree of freedom. I'll talk about it. क्या होता है degree of freedom? Let's say there is this particle, any monoatomic particle, only single atom, for example helium. In which of the directions can it move? It can move in this direction, maybe this direction, in the z axis as well. So these are the primary directions in which it can move. Of course it can move in any of the direction which is in between them, but that will be combination of two different motions, right? We are not concerned about that. We are just concerned about what are the maximum amount of uh, in, independent movements the particle can have. Of course it can have a velocity in the x direction, velocity in the y direction, velocity in the z direction. These three velocities it can have, and all these velocities individually should contribute to the kinetic energy of the body, right? So I can say that the number of ways in which it can possess energy in the form of kinetic energy is 3, and that is called degree of freedom. Degree of freedom. It means in how many ways it can move. How many ways it can move. So for monoatomic particles, the degree of freedom is actually 3. Now, uh, let's say the particle is here and it is going in this direction. Let's say I heat it up too much, but uh, this will also exhibit 3 types of vibrational motion, right? But one of the vibration motion will actually be in this direction itself. So will it lead to any another type of motion? No, of course not. That is why it is just added up in the primary velocity. But once a particle has a velocity in this direction at the moment and it vibrates in this direction, what will happen? It is a completely independent type of motion. That is why it will be added up in the degree of freedom. So let's say you have monoatomic particle, or yes, monoatomic particle. In this direction it can vibrate, and in the direction of outside the plane or inside the plane, these two directions it can vibrate if the energy is very high or the temperature is very high. So in those cases, the degree of freedom, which was initially 3, becomes 5. Why does it not become 6? Because vibration in this direction is sort of pointless. It doesn't add up in the um, actual independent motion of the body, because this motion becomes dependent on the original velocity of the body, which was in this direction. All right. That is why the monoatomic particles at higher temperature will have a degree of freedom of 5. What about diatomic particles? Diatomic particles, uh, yes, these two particles having a bond between them, a rigid bond, A and B. Now, the three motions, it can even have it right now in this direction or this direction, or the Z direction, X, Y, Z direction. These are the usual two, or usual three motions it can have. But while it is moving in this direction, can it also do a motion like this or this? It can, right? And let's say uh, it something like acts like this thing. This is the motion. So basically, it is a stick which is, of course, the center of which is moving upwards, but the stick is actually dancing like this. This is one of the independent moशंस the particle it can have. अगर इस टाइप का मोशन पार्टिकल ने किया, तो हम उसको डिग्री ऑफ फ्रीडम में ही ऐड करेंगे, राइट? क्योंकि उसके पास इंडिविजुअल एक और एस्पेक्ट आ गया मोशन का. सो दैट इज 1 डिग्री फ्रीडम. एंड और क्या कर सकता है? अगर ये पार्टिकल इधर जा रहा है, तो ये तो कर ही सकता है. while while see in this, it can also do something like this, right? ये वाला, राइट, कर सकता है, बिल्कुल कर सकता है. So this will add to another degree of freedom, but it cannot exactly. क्या क्या हो गया अभी? एक तो 3 ट्रांसलेशन मोशन हो गया, और ये पार्टिकल कैसे कैसे मूव करेगा? एक तो इस डायरेक्शन में, फिर इस डायरेक्शन में, और तीसरा जो डायरेक्शन होगा वो एक्चुअली इसके इनिशियल वेलोसिटी के साथ मैच कर जाएगा, राइट? सो दैट इज वाई इट विल हैव 5 डिग्री ऑफ फ्रीडम. A diatomic particle will have 5 degree of freedom, but at the same time, अगर ये हाई टेम्परेचर की बात की जाए, तो डायटोमिक पार्टिकल है वो वाइब्रेट किस किस डायरेक्शन में कर सकता है? ये तो ऐसे से करे, ऐसे से करे. ऑफ कोर्स इट इज इंडिपेंडेंट ऑफ द ओरिजिनल डिग्री ऑफ फ्रीडम. फिर ये ऐसे से भी कर सकता है, जेड एक्सिस में, आउट ऑफ द प्लेन, इनसाइड द प्लेन. बट अगर ये पार्टिकल, दो पार्टिकल ऐसे ऐसे वाइब्रेट करता है, वो तो रिस्ट्रिक्ट हो जाएगा, क्योंकि इसका एक पर्टिकुलर बॉन्ड लेंथ है जो कि उसको एग्जैक्टली फ्री मोशन नहीं करने देगा. इट विल नॉट अलाउ the bond of the particles between the particles will not allow the individual atoms to exhibit free vibrational motion between them, because it will change the bond length. दैट इज वाई यहाँ पर 7 डिग्री ऑफ फ्रीडम आ जाएंगे, क्योंकि 5 तो हमने ऑलरेडी डिस्कस कर लिए, एंड 2 फ्रॉम द वाइब्रेशन. सो एट हायर टेम्परेचर a diatomic particle will have 7 degree of freedom. For polyatomic particles, we will have formula for that. You don't need to remember these, but these you must remember. ऑलराइट, अभी ये हो गया। तो अगर ये हो गया है तो हम कुछ चीज़ें डिस्कस करते हैं। डिग्री ऑफ फ्रीडम, राइट। हाँ, अभी वापस आते हैं इस पे, क्योंकि हम यहीं पर डिग्री ऑफ फ्रीडम देखकर मैं वापस उस पे गया था, सो दैट यू आर एबल टू अंडरस्टैंड। नाउ हियर, एज पर द काइनेटिक थियोरी ऑफ गैसेस, जो भी हमने assumptions लिया था इसमें, द एनर्जी एसोसिएटेड विद ईच डिग्री ऑफ फ्रीडम ऑफ द पार्टिकल is actually half kT, where K is Boltzmann constant, and T is the temperature. And this is for 1 degree of freedom. If the particle is monoatomic at normal temperature, it will be 3 by 2 kT, because the degree of freedom at normal temperatures of a monoatomic particle is 3 by 2 kT. For a diatomic particle at normal temperature, it will be simply 5 into half kT, 5 by 2 kT. For higher temperature, for diatomic particles, it will be 7 by 2 kT, where K is the same Boltzmann constant, temperature, and the only thing is 7 by 2 or 5 by 2 depending on the degree of freedom. So each of the degree of freedom will have energy equal to half kT. Alright. Now this will result into some interesting observations, जैसा कि 3 टाइप ऑफ स्पीड देखेंगे हम पार्टिकल का, 3 तरह का स्पीड, और उसके बीच में डिफरेंस भी समझेंगे। फर्स्ट ऑफ ऑल, रूट मीन स्क्वायर्ड वेलोसिटी और स्पीड. It means, let's say the particle is going here, another particle is going here. If you take the average of them velocity, then it is often called velocity. Why we take root mean square is because if you add them up, the velocity will become zero, the net velocity of the system. That is why we take root mean square, so that each of the terms will tend to give you some non-zero value. सो RMS VRMS का फॉर्मूला होता है √3 RT/m. अभी ये तीनों में चेंजेस कर सकते हैं, कोई दिक्कत नहीं है. RT को रिप्लेस कर दिया प्रेशर से, फिर M को डिवाइड करना पड़ेगा V से, m/v, राइट. इसको इधर ट्रांसफर करो, RT को P में चेंज करना है तो V से डिवाइड करना पड़ेगा ना. अभी V से डिवाइड किया तो m/v बन गया डेंसिटी, एंड दैट इज वाई दिस इक्वेशन. In the same manner, you will play around with some terms. It will tend to become the both of three are equally useful. You should remember it, but this one is most commonly required. All right. Now, this is the VRMS. How we calculate it is a very lengthy procedure, but we just need to remember the results. No need to get into the derivations. Now, average speed. अभी एवरेज स्पीड को एवरेज लेकर जीरो क्यों नहीं होता? क्योंकि यहाँ पर वेलोसिटी की बात ही नहीं करते हैं. यहाँ पर वी टेक स्पीड. इसका भी स्पीड 3 है, इसका भी स्पीड 3 है, दोनों का एवरेज हो गया 3, 3. सो दैट इज कॉल्ड एवरेज वेलोसिटी, एंड उसका इक्वेशन होता है 8/पाई RT/m. सो इट इज बेसिकली √8/3 पाई into VRMS, which was 3 RT/m, and the value for that will be 0.92 VRMS. You should remember it that VRMS is greater than V average. All right, and there is this another V most probable. It takes into account the all the particles and their medians. All right, so most probable speed is nothing but 2 RT/m, which is 0.86. So can I say it is greater than V most probable? And here you have a simple relation between them, or comparison between them, so that we are able to understand what it is. इन सभी में VRMS इज द मोस्ट इंपॉर्टेंट, बट ऑल ऑफ देम आर इंपॉर्टेंट. डायरेक्ट क्वेश्चन आते हैं. Simply you if you remember the equation, you are going to solve it. If you don't remember what it was, whether it was 8 by pi, 8 by something else, you can forget the question in that case. Now, coming to specific heat capacity, we had discussed about the specific heat capacity in the last in the calorimetry part, in which specific heat capacity is basically, see, we have, let's say, uh, object of mass m, and at a temperature T, you want the temperature to be raised to T dash, then you will have to provide some heat, right? Now the heat that needs to be provided for raising the temperature is actually given by this equation. Q is equal to m c delta T, where m is the mass of the body, delta T is the change of temperature, and C is specific heat capacity. Heat capacity. In other words, specific heat capacity is the amount of heat which a system or maybe a material needs to be provided for raising the temperature by 1 degree Celsius, and that object is of mass 1 kg. So 1 kg का मटेरियल है, उसका टेम्परेचर एक डिग्री सेल्सियस से बढ़ाना है और 1 केल्विन से बढ़ाना है. उसको जितना हीट चाहिए वही होगा स्पेसिफिक हीट कैपेसिटी ऑफ द सिस्टम. बट देयर इज दिस थिंग, ये सब सॉलिड्स के लिए अच्छा लगता है कि स्पेसिफिक हीट कैपेसिटी वगैरह कैलकुलेट कर लिया. बट व्हाट अबाउट इफ दैट वाज अ गैस? इफ दैट वाज अ गैस, तब चीज़ें थोड़ी चेंज होती हैं. क्यों? क्योंकि यहाँ पर टेम्परेचर रेज करने से, यहाँ पर हीट देने से सिर्फ टेम्परेचर रेज होगा ये एग्जैक्टली नहीं बोल सकते हम. व्हाट इफ द some pressure is also increased? It can happen, right? Or some work is done on the system, some expansion is there, वॉल्यूम बढ़ गया. लो, तुमने टेम्परेचर बढ़ाने के लिए हीट दिया था, उसका प्रेशर बढ़ गया, उसका वॉल्यूम बढ़ गया. अभी ये सब प्रेशर एंड वॉल्यूम आर इंक्रीजिंग, दे आर नॉट जस्ट बिकॉज of the byproduct of temperature increase. No, many times it is the major driving force which increases pressure or volume itself. So we should take into account that the energy which what we are providing goes exactly into the changing temperature. But the gas के case में these two factors play a very important role in defining what will be the heat required to raise the temperature. अभी इसमें हम दो अलग टाइप ऑफ स्पेसिफिक हीट कैपेसिटी डिफाइन करते हैं. वन, कीपिंग द कांस्टेंट प्रेशर, एंड अनदर कीपिंग द कांस्टेंट वॉल्यूम. सो दीज आर द टू स्पेसिफिक हीट कैपेसिटी, और इनके बीच में रिलेशन भी होता है. Cp minus Cv is equal to R, and Cp minus Cv is a constant which is called gamma, which is very common in the chapter of thermodynamics. So I hope this was clear. Specific heat capacity, this is what we are talking about, specific heat capacity. And specific heat capacity के लिए एक फॉर्मूला होता है F by 2 R, और F by 2, एक सेकेंड, प्लस 1 R. ये होता है CV का और ये होता है CP का. ऑलराइट, ये डायरेक्ट फॉर्मूला है, वेयर F इज द डिग्री ऑफ फ्रीडम. उसका स्पेसिफिक हीट कैपेसिटी विद रिस्पेक्ट टू कीपिंग वॉल्यूम कांस्टेंट और कीपिंग प्रेशर कांस्टेंट इज डायरेक्टली गिवन बाय दिस फॉर्मूला. And since gamma is defined by, gamma is nothing but Cp by Cv, so it is directly defined as F by 2 plus 1 into R by F by 2. When you simplify this, you will get this thing. Gamma is equal to this much for polyatomic gas. And for individual gases, you can directly find out. For monatomic and diatomic, you can directly find out by this. See, say for example, monoatomic gas. Cp is equal to F by 2 into R, which is equal to 3 by 2 R. For Cv, it becomes F by 2 plus 1 into R, which is 5 by 2 R. And if you want to calculate gamma for monoatomic gas, it will become 5 by 2R. Sorry, this was I guess Cp and this was Cv. Sorry for that. Cp by Cv is equal to 5 by 2R divided by 3 by 2R, so it becomes 5 by 3. This is gamma for uh, monatomic gas. Alright. Okay, so right, this is 5 by 3, and in the same manner you can calculate for diatomic gas 7 by 5, which turn out to be 1.4, which is the most commonly used gamma for most of our problems. So even if you don't remember it, you are given that uh, uh, this is the diatomic gas and so are happening with that, and us question mein, if you need the data of gamma, you can directly plug 1.4 even if it is not given there. That will ease up your process. So that was for the monatomic gas. And yes, as a result of these velocities, as a result of individual velocities, the pressure is also exerted, right? And the pressure can be given in the format of 1 by 3 rho v RMS square, where rho is the density, RMS velocity we have exactly got here, from here. So you can even write it as 1 by 3 into rho into what was v square, 3 RT by m. 3 RT by m. Alright. So 3 gets cancelled out and you're left with rho RT by m. If you calculate using or if you simplify, try to simplify over with the, what was that, ideal gas equation, you will just end up with P. So there's no point on doing this. Just remember this part, it will be good enough. Now, relation between pressure and kinetic energy. See, kinetic energy तो आपने already find कर लिया था, half mv square, where vrms you can take directly, half mv square, right? Where vrms you can take. So that will become 3 by 2 pv or 3 by 2 ktn, where n is the number of particles. If you want energy for the uh, energy for the individual atom, that will be E is equal to 3 by 2 kt. As simple as that. So I think this was it, and this is the last thing which you are left with is the mean free path. This is talking about, let's say we have this block of gas in which gases are there. What you do is, since they are in random motion, right? You remember, they are in random motion, whatever direction they are traveling. So they must be colliding with each other. बीच बीच में एक दूसरे से टक्कर हो रही होगी ना, तो एक टक्कर के बाद let's say it has collided here with this particle and goes on to collide with another particle here. Now what is this average distance? It means the, अगर इंडिविजुअल एटम्स एक दूसरे में कोलाइड कर रहे हैं और दो कोलिजन्स के बीच में जो भी स्पेस बच रहा है, या फिर एक कोलिजन हुआ, अब उसके कितना आगे जाकर, उसका कितना लेंथ आगे जाकर फिर से कोलिजन होगा, इसको अगर हम प्रोबेबिलिटी के अंदर काउंट करें तो ऑन एवरेज कितना अमाउंट ऑफ लेंथ कवर करता है बिटवीन टू subsequent collisions, that is given by this formula, which is given as the mean free path 1 by 2 pi n d square अभी इसमें क्या क्या है, हाफ बाई 2 पाई n d²। अभी इसमें d क्या है, d है डायमीटर ऑफ इंटरेक्शन, मतलब कि दो अगर पार्टिकल्स आ रहे हैं एक साथ तो ऑफकोर्स एक दूसरे में एकदम चिपक तो नहीं जाएंगे, एक दूसरे का इलेक्ट्रॉन्स का बहुत ज़्यादा रिपल्शन होगा। सो वट एवर द डायमीटर ऑफ दैट यू कैन टेक अप हियर एज d²। एंड अगर इस इक्वेशन की बात की जाए तो दैट विल बी k इज द बोल्ट्जमैन कांस्टेंट, t इज द टेम्परेचर, बोल्ट्जमैन कांस्टेंट, टेम्परेचर, p is the pressure, under root 2 pi is the numerical value and d is the diameter of the interaction। मतलब कि दो इंडिविजुअल पार्टिकल्स जब कोलाइड हो रहे होंगे तो उस पूरे कॉम्प्लेक्स का डायमीटर कितना है मैक्सिमम फ्रॉम द वन एक्स्ट्रा। डायमीटर किसको बोलते हैं, मतलब कि एक एंड से दूसरे एंड, दैट इज द डायमीटर, राइट। दिस कैन बी कंसिडर एज द कॉम्प्लेक्स and the diameter of that complex will be from one end of one particle to another end of the another particle, that will be the diameter, and that is given, that helps you to find out the mean free path, the length of the mean free path. I think yes, under the I think this one I forgot about it. Avogadro's law. Avogadro's law is simple, that if you have two objects or two boxes in which the temperature is same, pressure is same, and the volume is same, these are called the uh, very standard conditions: temperature, pressure, and volume. In thermodynamics you will be using here and there, everywhere. So if for these two objects or these two boxes, temperature, pressure, and volume are exactly the same, and even if they have different atoms, for example this has helium and this has oxygen, then the number of atoms or number of molecules in the oxygen must be equal to the number of atoms of helium, molecules or atoms. All right, this is even applicable to the noble gases, which are usually single atomic. And there is this PV is equal to nRT that you must be familiar with, ideal gas equation. So I think that is it for this mind map. This was relatively small, and the most important part, these are the results that you need not be very particular about. You already know about this you must remember. And most important part is this one. You must remember all these three equations, and this one is very important, and this one. Rest of it you must go through, but they can be derived very quickly, so need not uh, burden yourself with the every bit of data that can be possible. So that is all for this mind map, and thank you.